let's learn section 3.3, measures of position. Now that we've learned measures of center, mean, median, mode, and measures of spread, standard deviation, variance, let's combine them so that we can properly assess where a data point is in relation to the others. So before defining terms, let's look at a motivating example. You can read question 1. And how would you compare Ted Williams' batting average and Rod Carew's batting average? Straight up, just looking at the raw scores, it seems Ted Williams has a better batting average. 406 is higher than 388. However, raw scores ignore the context of the rest of their data sets. So in this case, I should just say raw batting average score ignores the eras during which the two men played. Right, so for example, if Ted Williams played during an era where there were a lot of good hitters, and there were, then 406 may not be as impressive as 388 batting average might be if, for example, in 1977, there weren't as many good hitters, which there weren't. So instead, let's measure how well these players did relative to their peers. So instead, let's consider how far above the mean our batting averages are, right? So it turns out, you can crunch the numbers yourself, but the mean batting average in 1941 was 280, and the mean batting average in 1977 was 277. So I'll just do a little bit of subtraction. Let me get, okay. I guess I'll say, I guess I'll call this XW for Williams is going to equal 406 minus 280, and that equals 126. The score for Rod Carew is going to be 388 minus 277, and that equals 111. So maybe they're a little bit closer, but it looks like Williams is still superior. So Williams' batting average, this is the symbol for batting average, is still higher, even after considering mean. Okay, but what are the drawbacks to this method? Well, if we think about last section, spread is ignored. Well, how much could spread really affect this? Well, let's define a new term. If we just consider the mean of a standard deviation, that means only so much without the standard deviation. Now, we're headed in the direction of analyzing the normal distribution, and for this section, a lot of what we do will analyze the normal distribution. So remember, that's just the bell-shaped curve, symmetric bell-shaped curve. So we're going to denote the normal distribution with mean, mu, and standard deviation, sigma, like so. Be clear that is a sigma. Okay? If we use sample data, then we'll just call it X bar and S, right? We use English letters for sample data. So anyway, the z-score of a data point in X in normal distribution is the number of standard deviations that X is from the mean. Okay? This is extremely important. I will not give you this formula on any examinations or assessments. We have to know this. Here's the formula for the z-score. Z equals x minus mu. Right, so what we were experimenting with in solution B. But then we divide it by the standard deviation because it's the number of standard deviations from the mean. And if you're using sample data, or sorry, this is not x bar, so that's just raw score x. If you're using sample data, it's going to be x minus x bar all over s. Sorry, x is our data point, right? Anyway, just so you know, if we ever, there might be a time where we want to solve for x in terms of z. So if you multiply both sides by sigma and then add mu, you would get that x equals mu plus z sigma, or x bar plus zs. Just something to keep in mind. Not sure how much we'll use that in this lecture today, but it's good to know. Now, the only time we really consider the z-score is when we're talking about distributions that are approximately normal. They have to be approximately normal, or else we don't really consider z-scores, because we wind up using the empirical rule, okay, and other finer points, okay? So anyway, now let's go back to our problem with Ted Williams and Ron Carew. Now, it turns out, you can calculate this, the standard deviation in 1941 was 0.033, and 1977 is 0.027. Let's see if that changes our answer. So if we look at the z-score for Ted Williams, we're going to get 406 minus 280 all over 33. When we do that out, well, we know that that's going to be 126 over 33. And that's going to equal, let's see what we get. I guess we can bust open Google for that. You can do this in Excel if you'd like. You can also use Google. Google is actually a very good calculator. Just remember, we can't use this on assessments, at least not right now, right? Whoops. Oh my goodness gracious. 126 divided by 0.033, 3.82. Which is an unbelievably high z-score, right? It's almost 4 standard deviations above the mean. Now let's compare that to the z-score for Rod Carew. A 388 batting average minus 277, which is the league average that year, divided by the standard deviation, 0.027, right, which is 111 divided by 0.027. And this winds up being, well, let's find out, right? .11, somehow higher, over 4 standard deviations above the mean. You just never see this kind of performance, ever. This is unbelievable. So in this case, Carew's batting average is better if we account for both the mean and the standard deviation, and we consider z-score, because his batting average was more standard deviations above the mean than Williams's was. Okay? So z-scores are very, very important. If you learn any one thing from this class, let it be the z-score and its uses and its importance. Okay? Now, one thing that we can do is we can take any data set that we want and convert all of the raw scores into the z-scores. And it turns out it looks something like this. If we have a normal distribution, again, maybe it's not exactly normal, but it's roughly normal, and we have something like this, right, where the mean is one thing, standard deviation is the other thing, and we convert every single data point to its z-score. Well, let me first take something generic like this. Let me copy that guy. Maybe crop this guy a little bit. Crop this guy. And we're just going to stick it in. Just going to stick it in our notes. All right, and we will just copy this. Copy the photo. Stick it in our notes. Okay, we'll just put it right here. And then let's see what happens if we go back into Desmos. Oh, I might have lost it. It's okay. Get it back open. And now what we're going to do is we're going to standardize things. We're going to let the mean equal 0. And the standard deviation be equal to 1. Okay. So now we have something that's a little more spread out, for sure. Just in our case. Right? But it is still a normal distribution. There, now we can adjust on the fly. And so we still have a normal distribution, it's just standardized. And we're going to look at this in a few weeks. It's called the standard normal curve, right? So this is, I think this was mu equals point, I think it was, what was that? Looks like 0.2, no, looks like it's 2.8. And it looks like sigma, I think it was 0.45. Here we had mu equals 0, sigma equals 1. Okay? You can take any data set that looks like this, or maybe it's, you know, steeper or flatter. It will always have this standard normal curve. Okay? Just to let you know. All right, now let's do an example where z-score can be helpful, right? Sort of similar to the last one, but maybe a little more straightforward. We'll see. So we have 1-year-old and 2-year-old spotted flounder. We have a mean here, standard deviation there, mean here, standard deviation there. And we want to know who had the better catch, Harry or Sally. So it's impossible to compare two different kinds of fish, but using z-score, we can have an idea of maybe who did better, right? So the z-score for Harry is going to equal, what did he catch? 147 millimeter minus, what is it, 1-year-old, so minus 126 divided by 18, right? And this is going to be, what is that, 21 over 18, I think. Is that right? Which is, I think, 7/6, and we can just put that in a calculator, right? Put 1 and 1/6, and we'll say what that equals. Meanwhile, Sally catches a 200 millimeter 2-year-old, right? That's 162 divided by 28, and this gives us 38 over 28. Divide that by 2, we get 19 over 14. I'm not sure it's super clear which is bigger, but 19 over 14 is more impressive. Let's just find a calculator just to double check. Right, here we have 7 over 6, which equals 1.17, and 19 over 14, which equals 1.36. Okay, so 1.17, and this equals 1.36. So this means Sally's catch was more impressive because her z-score was higher. Higher than Harry's. Okay? Now, let's see. Dave, on the other hand, maybe Dave's just starting out or had a bad day or whatever. He claims he caught a fish that had a z-score of negative 1.2. So how long was that? Well, you could go ahead and use this formula that I said, or you could be like me and you just never remember it, but you always remember the z formula. So we know that z equals negative 1.2, which equals, what's it going to be? X minus, what he say? I didn't even say what kind of fish it was. Suppose it was a 1 year old. Okay? So that means that its mean will be 126 divided by 18. And that implies that x is going to equal 126 plus negative 1.2 times 18. Right. And we can just do this out. 126 plus negative 1.2 times 18. That gives us 104.4. millimeters. Now you might be wondering, hold on a second, why didn't you put millimeters or any sort of units for z-scores? Turns out z-scores are dimensionless. They don't have units. That's one of the nice things about z-scores. It doesn't matter what you're talking about. Z-scores are always, they're always a relevant thing. They always mean the same thing, regardless of the unit, regardless of the scale. So anyway, so this is how you measure not just the spread, but the position of data with regard to the mean. We also have ways of measuring position regarding the median, right? Now remember, the median is a purely positional measure, so we use other positional measures. We divide our data into, I guess I would say, quarters, or quartiles is really the term that is used here. Now, the range of a data set is really the difference between its highest and really, I should be saying, the range of a data really is just the highest value minus the lowest value. And we could just get rid of this. Okay? The interquartile range, which is denoted IQR, because no one's writing that every time, is the difference between the values Q3 and Q1. Median is labeled Q2. So there is a procedure in the textbook for finding Q1. Let me just be clear about what this means, right? If we have a data set, okay? Suppose this is the min. This is the absolute lowest point. And this is the max, the absolute highest data point. We would divide our data first in half, right? This is the median. All right. Median. We call this Q2. Why we call this Q2? Well, because we further divide our data into quartiles. Okay? And technically speaking, you could consider the min to be Q0, and you could consider the max to be Q4, if you wanted. You never really hear these. I've never heard this, really. But I have heard Q2 be referred to as the median. Okay? So anyway, there's this whole procedure. It's just kind of annoying looking because of how technical it is. I will go ahead and show you what the procedure is, just so you have it. But in practice, what's the real procedure going to be? The real procedure is going to be put the stuff into Excel and just look at what Excel spits out. That's going to be the real procedure. But that said, and this is college, we should at least see what the technical procedure is. So I will put it in the notes. I will paste it in there, and you can look at it to your heart's content. Let's look at quartiles right here. All right, here you go. Oh, let's try that again. There we go. There, and then there. And we shall copy and delete. There we go. So there's our procedure, okay? Now, anyway, another important, so you might notice that there are 1, 2, 3, 4, 5 values here that are important, and so the 5 number summary of a data set is the set, and really I should say the sequence, because it is ordered. I guess I'm not going to call it Q0. No one calls it that. They call it the min, Q1, Q2, which is the median, Q3, and the max. Okay? That's what the 5 number summary is. So if I ever ask for the 5 number summary, it's just those 5 numbers in order. All right, so let's see if we can get the 5 number summary of batting average of qualified MLB hitters in 2025. We've used this before, so if you've downloaded it, then you can just get that out. Copy the column. Let me just show you the column really quickly. It is this guy. It is the one that begins with 0.331. Okay. So what you can do is you can copy it. All right, just bring all that down here. All right, copy that. Go to our Excel program, right, which we can find in my classes under the syllabus module. Anyway, just paste it in there. It's technically, this isn't going to be completely right because I think there are more than 100 data points, and this allows us to paste only 100, but whatever. This is pretty good. So anyway, it looks like the mean is roughly, it looks like it's 265. Standard deviation is, 22. But we're actually interested more in the 5 number summary, right? So I'm looking at these guys. Maybe I should go and paste this in here. See if it's going to like that. Oh, it does like that. Very nice. So there we go. Okay. Now, here's something where I say, let's see if we can create a box plot of the data. This is also known as a box and whisker plot. I think the book uses the term box plot. I forget, honestly, but you'll see both. So here's the question: what do boxes and whiskers represent? Well, let's see. Yeah, I think I get into how to create a box plot there. Well, first I just want to show you something. If we go to Excel and we go to, let's see what kind of, do we have a place for box plots? Because I thought we did. Maybe not quite here, but let's see. Let's see, I really thought there was a place where we had, maybe not, maybe we don't have box plots here. Let me just check something real quick, because I think I might be able to find a box plot. Just give me one sec. Let's try this guy. Let's see if this is any better. Well, if not, well, then that's okay. We'll worry about that a bit later. But anyway, we don't actually need Excel to do this. We can just do this by hand. So here's how we're going to do it. We draw an x-axis. You can also draw this vertically, but we're not going to do that. So we're going to have our min value right here. So let's say that we're going to begin at 200 because our min right here is 214. And then we're going to have our max value maybe right here. This is 331. And then maybe this will be like 350 or something like that. And so we'll say that this is 250. Or maybe we'll say this is 225. Maybe that's not perfectly to scale. Maybe it's more like here, 225. This is 250. 275. 300. Delete this guy, right? 325, and then this is 331, and that's 350, okay? So anyway, what do? We look at the first quartile, which is 251. That's about here. And we draw sort of a line like that. Third quartile, 278, that's about here. We draw a line right there. Okay? And then we just connect them. Okay? And then we draw a line for the median, 263. It's basically right in between them. Right there. Okay? Whoops. This is 263. Okay? We also make a note of our min and our max. And what we're going to do, we're just going to draw little lines right here. And we're going to draw these big whiskers connecting our boxes to these min and max values. Okay? This is our box and whisker plot. Okay? And maybe we should label our axis, right? MLB average in 2025. Okay? So anyway, what's the range in the IQR of the data? Well, the range is going to equal 331 minus 214, which equals 117. The IQR equals Q3 minus Q1, which equals 275 minus 251, which equals 24. Okay, so there's that. So before we formally define a box plot, we define an outlier. Now, we won't worry too much about marking them because we don't have the graph right now in Excel. But just in general, an outlier is far to the left or far to the right of a data set. Now, we are going to formally define an outlier to be a data point less than Q1 minus 1.5 times the IQR, or greater than Q3 plus 1.5 times the IQR. And where do we get this from? Well, it's kind of arbitrary, but it's what statisticians have defined, so we're going to use it. Okay. Now, a box plot is a graph that illustrates the 5-number summary. Right, as well as the outliers. So here's how you draw a box plot. Step 1, finds the 5-number summary of your data set. Find all outliers. Step 3, draw and label your x-axis. Next up, and this includes marking the 5-number summary. So I'll say draw medium vertical lines above Q1, Q2, which is the median, and Q3. And connect the Q1 and Q3 lines to form a box containing the Q2 line. Next up, draw small lines above min and max. And I'll say connect, whoops, min to Q1 and Q3 to max with horizontal lines. All right, and that's how you create a box plot. Now, just one last thing before we sign off. A finer way to portion data is percentiles. The nth percentile of a data set is the data strictly less than n% of the data, and, or sorry, I lied. Is the data, I'm so sorry. The nth percentile is the data greater than n% of the data and less than the remaining 100 minus n%. So, for example, if Kevin scores in the 97th percentile, 3%, right, because that's 100 minus 97%, which equals 3%, did better than Kevin. All right. Now, looking at the batting average data, what average is roughly in the 71st percentile? We're just going to eyeball it. All right, if we go to the descriptive stats, we can't really order these, but we can just sort of look at things and say, well, if the third quartile was 278 and the median was 273 or 263, then probably 71st percentile is going to be close to 278. Okay? So we'll just say, since Q3, the 75th percentile is 278, the 71st percentile is roughly I'll just say 275. Okay. And the percentiles Q1 through Q4 are really, Q1 is the 25th, Q2 the median, that's got to be the 50th by definition. Q3 I mentioned above is the 75th. And Q4, which really, really we're talking about the max here, We never say the 100th percentile because a data point can never be bigger than itself. So technically speaking, it's never bigger than 100% of the data point. We only ever say 99th percentile. But we could talk about the min, and that would be the 0th percentile. That does make sense. All right, and that's all we've got for today.